Swayam Prabha. Digital India. Educated India.
Okay, so we talk about another symmetric key encryption primitives, which is stream cipher. So Alice and Bob is having the common key K in the symmetric key scenario. They have a common key K. Now we have seen in block cipher they have a we have a function which is take the L bit input and give the L bit output, that is the blocks. Now in stream cipher, this is also another primitives of symmetric key crypto system. In stream cipher, usually the plain text are in binary bit, say 0 1 bits. So binary bits. And we have a key stream which is basically taking the, we have a key stream generator which can generate the key stream bit, which is also a binary bits, 0 1 bits, 1 0 1 1 0 1 like this. So this is key stream bits, and we do the bitwise XOR with this 0 1 1 0 0 like this. This is the ciphertext. Okay, so this is a stream cipher, typical stream cipher. So they have a common key K. So from this K, one has to get this key stream. So we will talk about some key stream generator. So it will give us the key stream. So this is basically like this. We have this plain text xi and so on, and we have the key stream k1, k2, ki. These are the key stream bit. Now we do the bitwise XORing, and we get C1, C2, Ci and so on. So Ci is basically Xi XOR with Ki, ith bit of the plain text XOR with the ith bit of the key stream. So there should be a what is called key stream generator, which takes this key, the secret key, and should able to generate this k1, k2, ki and so on. And this we are going to XOR with this plain text bits and get the ciphertext bits C1, C2, Ci and so on. And this Alice is sending to Bob C1, C2, Ci and so on. So this is the encryption. Okay, now how Bob will decrypt it? Bob is receiving this C1, C2, Ci and so on. So Bob has to get back the message x1, x2. So this is the message x1, x2, xi and so on. So what Bob will do? So Bob is having this C1, C2, Ci. So Bob also has to run the same key stream generator and get the this key stream bits ki and so on. So Bob will simply XOR and get x1, x2, xi and so on, because this Ci XOR with Ki is basically Ci is nothing but Ci is nothing but xi XOR with Ki, and this is XORing with Ki. So Ki is getting cancelled. This is Xi. So we are getting the Xi basically the ith bit of the plain text. So this is the decryption. This is the decryption. Okay. So now the question is how we can get this key stream bit. So we will take some example of key stream bit generator. One is LFSR, linear feedback shift register. But before that, let us analyze this nature of this key stream bit. So this is called stream cipher. Okay. Now So, in stream cipher basically we need to generate the key stream. So, we have this plain text bits. So, one has to generate the key stream, okay, and then we will do the XORing to get the CIs, I mean C1, C2, CI. So, CI is basically, now if you have a coin, then you can generate the key stream bit by tossing the coin. So, if we get a head, we will put it 0, if we get a tail, we put it 1, just keep on tossing a coin, we will get a key stream. Okay. So, now we will define the notion of what is called Shannon notion of perfect secrecy. Shannon notion of perfect secure cipher or perfect secrecy, RECY. Okay. So, Shannon notion is telling if the probability of plain text given the ciphertext is same as probability of plain text, and this is true for all plain text and all ciphertext. Okay. So, that means, so ciphertext is public, ciphertext is seen by anybody. So, this is transmitted over the public channel. So, it is seen by the Oscar. So, by seeing the ciphertext, if we are not getting any information about the plain text, if this conditional probability is the basically the unconditional probability of P. So, that means we are not getting any advantage of knowing the ciphertext. So, then we call our cipher is perfectly secure cipher, and then our cipher is called one time pad. If we have a stream cipher which is having this property, like if probability of a plain text bit given some ciphertext bit is same as probability of plain text bits. That means, we are not getting any advantage of knowing the ciphertext. Okay. And this can be achieved if this KIs are truly random bits. Truly random bits means, so KIs are binary bits, so it could be 0 and 1. If KI is 0, is half, if same as probability of KI is 1, then it is called truly random bit. And then we will see if our Ki is satisfying this truly random bit sequence. If we have a truly random bit sequence, then we can achieve this Shannon notion of perfect secrecy, and then that stream cipher is called a one time pad. Okay. But the question is whether we can achieve that, is it possible to have a truly random sequence or not. That is a because see we cannot, we are tossing a coin and head tail. So, we cannot make a coin where it is a totally unbiased coin. So, that means probability of head cannot be equal to probability of tail. So, anyway we will be using some algorithm to generate the key stream. So, that never gives us a truly random sequence of the key stream. So, that is why it is called pseudo random sequence. We will come to that, but before that let us prove this. If our key stream as a key stream bit is truly random bit, then we achieve the Shannon notion of perfect secrecy. So, let us try to prove this, and then that is called one time pad. Okay. Suppose we are encrypting a single bit. So, our X is, suppose we are doing 1 bit encryption. So, we have a message x which is a single bit, and we generate a key bit k, and we XOR this and we get a C bit. So, C is basically x plus k, or we can say P over here, plain text is a single bit. So, P XOR with k. So, this is the single bit encryption, and P is the 1 bit plain text, k is 1 bit key stream, not stream, 1 bit key generated from the this secret key, and C is the 1 bit ciphertext. Now, suppose this is a truly random bit k. So, that means suppose probability of this is same as probability of k is equal to 0. So, that means k is a truly random bit. Then we want to prove that this is achieving the Shannon notion of perfect secrecy. That means it is a one time pad basically. So, to show that, let us have some prior distribution of P. Suppose probability of P is equal to 0 is 0.6, probability that P is equal to 1 is 0.4. This is the prior distribution of the P. Okay. So, now we want to find out this probability of say P is equal to 0 given C is equal to 1. Okay. So, if we can show that this is probability of P is equal to 0, then we are not getting any advantage of knowing the ciphertext. Similarly, we have to show the all possibilities. P is equal to 1 given C is equal to 1 is equal to P is equal to 1. This we have to show, and probability that P is equal to 0 given C is equal to 0 is basically probability that P is equal to 0, and last one is probability that P is equal to 1 given C is equal to 0 is basically probability of P is equal to 1. So, if we can prove all these statement, then we can say that probability of x given y is basically probability of x, and this is true for all x from the plain text and for all y from the ciphertext. And then we say we are achieving the Shannon notion of perfect secrecy. So, we will try to prove only one, then remaining you can try at home. So, let us try to prove this probability of this is basically probability of x equal to P is equal to 0. Okay. So, this is a conditional probability. So, this is basically probability of A given B is basically probability of A intersection B divided by probability of B. So, this is basically probability of C is equal to 1, and this is basically probability of P is equal to 0 and C is equal to 1. Okay. So, this can be written as, so by Bayes theorem, I mean total probability rule. So, probability that P is equal to 0 comma C is equal to 1, and probability that P is equal to 0 comma C is equal to 1 plus probability that P is equal to 1 comma C is equal to 1, because P can be 0 or 1. So, this is the total space. So, this way we can write. So, this can be written as probability of, so this can be C is equal to 1 given probability of P is equal to 0 into probability of P is equal to 0 divided by, so again this can be written as probability of C is equal to 1 given P is equal to 0 into probability of P is equal to 0 plus probability of C is equal to 1 given P is equal to 1 into probability of P is equal to 1. Okay. So, just the total probability rule. So, this we can just calculate. So, probability of C is equal to 1, P is equal to 0. This is same as, so we are XORing. So, this is same as K must be 1, because if the we are XORing. So, this is 0 means this is 0. So, this is 1 means K has to be 1. So, this is same as probability K is equal to 1. So, this is equal to, or maybe I can write here. So, I can just write here. So, this is equal to probability of K is equal to, K must be equal to 1 into probability of P is equal to 0. Now, this one probability that P is equal to 0 and C is equal to 1, same as probability of K is equal to 1. This is probability that K is equal to 1 into probability that P is equal to 0 plus probability of K is equal to 0 into probability of P is equal to 1. So, if you just put the value, this is basically half into 0.6 divided by half into 0.6 plus half into 0.4. So, this is basically 0.6, which is same as probability that P is equal to 0. Okay. So, basically this we achieve probability of P is equal to 0. So, similarly other probability calculation we need to do, and then we can convince that probability of a plain text given the ciphertext is basically same as probability of plain text. So, we are not getting any information about the plain text by knowing the ciphertext. So, this is basically, so provide if our key stream bit is truly random bit, then this will give us a one time pad, and this is perfectly secure cipher under the notion of Shannon. But this is not possible in practice, because in practice we will use some algorithm to generate this key stream bit. So, there we cannot achieve this this truly random bits for KIs. So, that is why it is called pseudo random bit generator. So, this is the result where we can say if our key stream are truly random bit sequence, then we can achieve the Shannon notion of perfect secrecy, which is not possible in practice, which is impractical. So, truly random sequence, random number generator is not there. So, we have then we say that sequence we are getting from a key stream generator is called pseudo random bit generator. Okay. So, pseudo random sequence generator, pseudo random sequence generator. Okay. Because we cannot have a random sequence generator, that K1, K2, key stream are a sequence. So, we cannot have a, so we need to, so this is the key stream generator, generator. So, this is taking the key and it is giving us the key stream K1, K2, Ki and so on, depending on the size of the plain text. Now, if this all the Ki's are truly random bit, then this generator is called a truly random sequence generator, this is sequence generator, but which is not, and then it will achieve the, it is basically one time pad and it will achieve the Shannon notion of perfect secrecy, but this is not possible in practice. So, we call this generator, any generator of key stream is called pseudo random sequence generator, and we will see how good this sequence is. If we have a generator, key stream generator, we will see how good means how much randomness is there. So, those we have to test, some randomness test we have to do. So, those are basically some necessary test for a truly random sequence. So, those properties a truly random sequence must have. So, if we are getting a sequence, if we take a period of that sequence, if we run some test and if we pass that test, then those tests are basically necessary condition for a truly random sequence. If we have a random sequence, truly random sequence, those properties it must have. Okay. So, anyway, we will discuss those. So, let us just have a let us just have a key stream generator. So, one key stream generator is LFSR, it is called linear feedback shift register. Linear feedback shift register, or in short LFSR. So, it is basically a register. Register means basically a collection of flip flops. Okay. So, we can take an example, a 4-bit LFSR is basically we have a 4 flip flop which can store a single bit of information. Okay. So, this is these are all can store a 0-1 bit, 1 bit of information it can store, and it has some connection like this. Okay. So, these are all flip flops. So, it has some connection like this. So, a connection could be somewhere else also. So, these are called feedback bits. So, this position and this position is contributing in the feedback. So, what we are doing in each clocking we will output 1 bit, and then so this bit will come here, this bit will come here, this bit will go out, and that is our key stream, and this feedback bit will be calculated by this connection. Wherever we have connection, this suppose we have initially we have say 0 1 0. Okay. Suppose this is the initial state of the LFSR, and this may be the key shared between Alice and Bob, the secret key shared between Alice and Bob. So, we fill this by the initialization of this LFSR, and then what we do, we just clock it each time. So, for the first time in the first clock 1 will come here, 0 will come here, 1 will come here, 0 will go here. So, this is the K1 key stream bit, and this will be filled, this is linear feedback shift register, we are shifting, and this will be filled by these two positions. So, this is 1, this is 0. So, if we XOR it will be 0. So, this is at first clocking. In the second clocking, this will come here, this will come here, this will come here, 1 will be going out. Okay. And again, so now this is the state. Now, again this and this will be XOR and this will be put it here. Now, again this will be like this. So, this will come here, this will come here, this will be here, and this 0 will be going here as a key stream, and again we have these two. So, this and this. So, it is 1 basically. This and this will be XOR. So, like this. So, this is the key stream bit. Okay. So, this is an example, this is a just 4-bit LFSR. We have a general L bit LFSR, we will talk about that, but this is the how. So, this connection could be here, then we have a different LFSR, okay, and it has nice relationship with the polynomial. So, this we denoted by 1 plus, so here we have a connection x and this is x square, no connection, so x square won't come, this is x cube. Okay. So, this is the polynomial corresponding to this LFSR. Okay. Now, if we have a polynomial like this 1 plus x square plus x to the power 4, then what is the LFSR corresponding to this? Then we have, so this is basically x position x square, so we have a feedback over here, and then x to the power 4 we have a feedback over here. So, this is the LFSR corresponding to this polynomial. So, if we have a LFSR, we can have a polynomial 4-degree polynomial, or if we have a polynomial, then we can construct a LFSR. Okay. And if this polynomial is happen to be a primitive polynomial, we will talk about primitive polynomial, then this will give us a full sequence, this period of this will be full if this polynomial is a primitive polynomial. So, now let us talk about general case L bit LFSR. So, this is just an example of 4-bit LFSR. So, this is a key stream, this is an example of key stream generator. So, it is generating the key stream. Okay. In L bit LFSR, we have basically instead of 4-bit, we have L bits. So, we denote this by states S0, S1, or maybe we can start with 1, S1, S2, S3, SL. So, these are all flip flops. Okay. Now, we have a, so we will have a connection like this, we will put C1, then I will explain, sorry, we will have C2, okay. So, we will have C3 like this, and then for the SI, this is the ith, so we have CI. And these are, for all of this we have like this CL dot 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 dot. So, these are all okay. So, these are all this feedback and this is going here. So, this C1, C2, CL are either CIs are either 0 or 1. If CIs is 1, then that corresponding state or corresponding field will be contributing in that feedback. Okay. So, for example, this case this is C1, this is C2, this is C3, this is C4. So, for this case C1 is 0 because this is not contributing. If C1 is 0, this is the AND gate. So, that means whatever value it is having, it will be 0 only because C1 is 0. So, for this case C1 is 0, C2 is basically 1, C3 is 0 and C4 is 1. And here we have this key stream. Okay. So, this is one example. So, this C1, if C1 is 1, then that corresponding field is contributing in the feedback, otherwise it is not. And the LFSR corresponding to the and the polynomial corresponding to this is basically 1 plus C1x plus C2x square plus C3 x cube like this CL x to the power L. So, this is the polynomial corresponding to this LFSR. Now, for this LFSR, so it is just basically 1 plus C1 is 0, so C1x won't come, C2 is 1, so x square, C3 is 0, so it will not come, C4. So, this is the polynomial corresponding to this LFSR. Okay. But this is the we can just draw this using this AND gate, because if the C1 is 0, then this is always 0 no matter what is the value is having over here, and if C1 is 1, then this will pass whatever the value over is here, because in the AND gate if this is 1, then if we have x, this is basically x. So, whatever value, if it is 0 it will pass 0, if it is 1 it will pass 1. So, whatever value over here is, that will be the going there. So, that is that means this corresponding field will be contributing in the feedback. So, we will take a quick example where we have this we want to generate the key stream. Okay. So, suppose we take the polynomial like this 1 plus x to the power 4. So, that means our LFSR is this. So, 1 is there and x to the power 4. So, this is there. This is our LFSR. Okay. So, only these two state are contributing in the feedback. Okay. So, this is we want to see. So, this is a primitive polynomial. So, we want to see whether we are getting a full sequence or not. If you start with any initial state. So, that is basically the secret key shared between Alice and Bob. So, suppose we start with say some 0 1 1 0. So, suppose this is our this is the secret key k shared between Alice and Bob, and they are using this LFSR as a key stream generator in order to encrypt their plain text. Okay. So, now if we run this, so in the first shot this will come here, this will come here, this will come here, 0 will be out. And what about this? This will be basically XOR between these two. Okay. So, this is the first step, and next we will have, so this is basically this and this, we have 1 0 0. So, this will come here, this will 1 1 like this. So, like this if you continue, we will be getting like this 1 1 0 0 1 0 0. Then we have again this 0 1 1 1 1 0 1 0. So, this is basically 16 clocking. So, this is basically this sequence key stream is basically we are getting 0 1 1 0 0 1 0 0 0 1 1 1 1 0 1. So, this is the full sequence 16 period 15. So, next we will talk about the if we have a, so this is one way of generating a key stream. So, this is a key stream generator LFSR basically, and if we choose the polynomial is primitive polynomial, it is giving us the full sequence, and it will satisfy some nice randomness property. So, it will satisfy some necessary condition of the random sequence. So, those are called randomness test. We will talk about those in detail. Thank you.